Okay, Jesse, I said I would be sending you a video on just anything we didn't cover in class. So this was week 2, February 14th. We covered lesson 37. We covered lesson 38, but we did not cover lesson 39, so I'm going to go over that right quick. There were 4 theorems that we covered. Theorem 39.1, it says if one side of a triangle is longer than another side, then the angle opposite the first side is larger than the angle opposite the second side. So you can see here that if we're given side BC that's longer than side AB, then we can know that the angle opposite BC is greater than the angle opposite AB. Or the second theorem changes it the opposite direction. It says if one angle of a triangle is larger than another angle, then the opposite side of the first angle is longer than the opposite side of the second angle. That means if given that the measure of angle A is larger than the measure of angle C, that means that the opposite side of measure of angle A is longer than the measure of the opposite side of angle C. There's also the exterior angle inequality theorem that says the measure of an exterior angle, which A here is an exterior angle of the triangle ABC, if that exterior angle, it's just saying that exterior angle will always be greater than the measure of either one of the remote interior angles. And the third theorem is called the triangle inequality. It says the sum of the lengths of any 2 sides of a triangle must always be greater than the length of the third side. So take any 2 sides of the triangle, A plus B, it must always be greater than the third side, C. Okay, let's try to solve this problem here. This was number 13 in lesson 39 that you got incorrect. It actually comes from lesson 32. It says find the centroid of the triangle with vertices at 0, -2, 0, -6, and 2, -4. The first thing we have to remember is visualize what is a centroid and how do you find that. So if you go back and you remember from lesson 32, you find the centroid, which is it's like a point that's related to a triangle. And you find that centroid by finding the intersection of the medians of a triangle. And then you have to remember what is a median of a triangle. A median is a segment that goes from a given vertex of a triangle to the midpoint of the opposite side of that triangle. And once you find that median, you have to find at least a second median that crosses the first median, because wherever those 2 medians cross, and in fact all 3 medians will cross in the same place, but you only have to find 2, wherever they cross, that will be your centroid. And you'll have to find that by solving a system of 2 equations and 2 unknowns. But you have to have the first equation being one of the medians and the second equation being another median. So let's go ahead and draw this triangle and see what it looks like. So here is a Cartesian plane with the X and Y axis. This one might need to be a little bit longer. Okay. So we've got X and Y axis. Let's plot our points. We have 0, -2. So that would be -1, -2. So there's one point, A. I call it A at 0, -2. The next point is 0, -6. So 2, 3, 4, 5, 6. So this is point B at 0, -6. And then we have point C at 2, -4. So this is C at 2, -4. Okay, I'll blow this up a little bit larger so you can see it. And so let's go ahead and connect our sides so you can see this triangle. And let's think through this. If I were to find the median of A, I would start at vertex A and I would go down, and the opposite side is segment BC. I would try to find the midpoint and I would draw a line, and that's a median. So I need an equation for that line. But I need at least two medians. So let's look at point C. If I started at point C, I would need to find the midpoint of segment AB so that those two segments are equal, and then I would draw a line. So I need an equation for that. I don't really have to find the median at B. I could. It will go through where those two lines are crossing, but it's not necessary, so I'm not going to worry about it. So I'm going to go over here. Let's first find the median at C because it looks easier. So to find the median at C, the first thing we have to do is we have to know what is the midpoint. I'm not going to write midpoint. I'm going to just say the midpoint of segment AB. Okay, so we have to know what is the formula for midpoint. The formula for midpoint is you take the sum of the x-coordinates from point A and B, divided by 2, and you take, basically you're taking the average of these coordinates. So take the sum of the y-coordinates divided by 2. So we might need to go over here and look at these points. There's the coordinates of point A, there's the coordinates of point B. I'll make it smaller so we can see it. So we're going to go over here and say, okay, well, add the x coordinates, 0 plus 0 divided by 2. Add the y coordinates, which is negative 2 plus a negative 6 divided by 2. And that equals 0 divided by 2 is just 0. And negative 2 minus 6 is negative 8 divided by 2 is negative 4. So that's I'm going to go ahead and label it here. That is 0, negative 4. The next thing you do after you find that, now you have to come up with an equation of that line. So I need an equation of the median. And we always find it by just writing our general equation of the line. So what I need is where does it cross the y-axis, the y-intercept, and what is the slope? Well, the slope of the median is easy because it's just you take the change in y coordinates over the change in x coordinates. So you're looking at these coordinates. I'm going to do a different color. You're looking at, wait, I want that to be smaller. Let's see, how do I make that? I don't know if I can make that smaller. Yeah, this coordinate and these coordinates. So that's what I'm looking at. So I'm going to put it in pink over here actually so you can see it. This right here is related to those. Okay, so the change in y will be negative 4 minus a negative 4 over 0 minus 2. Negative 4 minus a negative 4 is negative 4 plus 4, which is 0 over negative 2. So the slope is 0. And that should make sense because this is a horizontal line. So horizontal lines have a slope of 0. And do I need to figure out where it crosses the y-axis? Can I already see where it's crossing the y-axis? I mean, basically, you can see that it's crossing the y-axis at y equals negative 4. So my equation of this line is y equals negative 4. That's what my b is. B here, this b is negative 4. And you can see it over here, negative 4. So that's my first equation. Now I'm going to put a box around it because I'm going to use that in a minute to solve for my system of equations. So I drew the median that goes from vertex A to the midpoint of segment BC. I drew it in orange, so I'm going to write my solution over here in orange. So I need the median equation at A, at vertex A. So that means first I need to know what is the midpoint of the opposite, which is segment BC. The midpoint of that segment. So I'm going to use B and C coordinates. So I'm going to add up the x coordinates, which would be C is 2 and B is 0 over 2. I'm going to add up the y coordinates. C is negative 4 and B is negative 6, and divide it by 2. 2 plus 0 is 2, divided by 2 is 1. And then negative 4 minus 6 is negative 10, divided by 2 is negative 5. So I'm going to go over here and put that this is my midpoint. It is 1, comma, negative 5. Okay, so I'm going to do, the next thing I need to do is get an equation for this median that went through A. And I need some y equals mx plus b. So I need an m, a slope, and a y-intercept. The first thing to find is your slope, because I have two points on that median. I have the point that goes through A, and I have the point that goes through the midpoint of BC, which is 1, negative 5. So my slope will equal the change in y. So I'm going to say, I'll start with my midpoint, which is negative 5, and I'll go to my negative 2 in the A vertex. So it would be minus a negative 2 over the change in x, which would be in the midpoint would be 1, minus 0 in the A. So what does that give me? Negative 5 plus 2 is negative 3 over 1. So my slope is negative 3. So now my equation becomes y equals negative 3x plus b, because I plugged that in for m. But I still need to know what is b. Well, b can be found because all I have to do is take either one of these points, 1, negative 5, or 0, negative 2, because they both intersect or go through the median line. So I'm going to choose the A since it has a 0, so it'll be easier. So I'm going to say that the y is negative 2 and the x is 0 plus b. That cancels, so I see b equals negative 2. So my equation becomes y equals minus 3x plus, well, minus 2. I don't need plus. Minus 2. So I'm going to box that in because I'm going to now use those two equations that are boxed in to solve my system. So to find the centroid, solve the system of y equals negative 4. That's one median that went through C, and the other one, y equals minus 3x minus 2, that went through A. Well, we already are given that y equals negative 4. So I know that my centroid will have negative 4 as y. But what will my x value be? So I plug in, I use substitution, and I plug in negative 4 for y in the second equation, and I still have minus 3x minus 2. I'm going to solve for x. Add 2 to both sides. That gives me negative 2 equals minus 3x. Divide both sides by negative 3. This gives me x equals positive 2/3. So 2/3 comma negative 4 is my centroid. So I could go ahead and label it over here, and I could say that is 2/3 comma negative 4. And that's how you solve to find the centroid. Okay, the next problem is number 15 from lesson 39. And it says, using the diagram, find segment MN in terms, that should say in terms of x. If the segment NO has a value of 2, the segment OP has a value of 4x, and the segment NP has a value of x plus 7. We are going to use theorem 38.1. Oh, did I forget to go? Oh, that was 38.1. Let me go back. Let me read it. I wrote it down somewhere here. 38. Hold on. 38. Oh, here it is. This is 38.1. We did do this in class today, but we learned that theorem 38.1 says that if a line bisects an angle in a triangle, so here we've got MN, and it's bisecting this triangle, that means this angle is equal to that angle, then that line that bisects the angle divides the opposite side proportionally to the other two sides of the triangle. So that means that this segment divided by this segment will be equal in ratio to this segment divided by that segment. So that's what we're going to apply to this problem here that we're doing. So this is going to be pretty easy. Since we're told, we can see this picture that MO bisects this triangle, then we know that that line will actually divide segment MN over segment NO. So this segment divided by that segment will equal this segment divided by that segment. So that will equal MP divided by OP. That's based on the theorem. Now let's plug in values. We know that MN is what we're looking for. The one that we're looking for is MN. So that's what it says, find MN. So we're going to leave MN as is. Whoops. MN. OP is 2. MP is x plus 7. And OP is 4x. And now we're going to cross multiply. Okay, we're going to cross multiply like that and create a new equation that's equivalent. So this would be MN times 4x equals 2 times x plus 7. So that's an equivalent equation. And now I'm going to divide both sides by 4x so I can solve for MN. So those cancel. So I have MN is equal to 2 times x plus 7 over 4x. But I can see that 2 goes into 2 one time and 2 goes into 4 two times. So now this simplifies, and MN equals x plus 7 over 2x. Okay, so that's lesson 39, and is going right now. But we didn't cover anything of lesson 40 because I didn't have any homework to show from. This is what it's talking about, finding perimeters and areas of composite figures. The concepts in lesson 40 is just that a composite figure is a plane figure or a two-dimensional figure that has simple shapes. It's composed of simple shapes. It may be more than just a square, but it may look like a square with a triangle attached to it. So you can break a composite figure down into simple shapes. A perimeter of a plane or 2D composite figure is the sum of the lengths of its sides. And then there's two postulates that says area congruence. If two polygons, and that a polygon is just a multi-sided figure that has no curves, but that's a closed figure. So if two polygons are congruent, then they have the same area. And then the area addition postulate says the area of a region is equal to the sum of the area of its non-overlapping parts. So like in this diagram, you see this composite figure that's composed of two triangles and a rectangle. So the total area would be the sum of the first triangle plus the second triangle plus the rectangle. Okay, since there's no homework, there's nothing for me to go over. I didn't really plan on it, but after lesson 40, there was also an investigation 4, And I realize that the investigations are very important to cover. So you should be doing those at home because they do add new theorems that you don't get anywhere else. For example, this is going to be applied in your homework problems, in the tests, but you can see in this problem that there is a theorem 41 and a theorem 42. So you can see the number 40, that means this investigation goes with lesson 40. So you should be doing these investigations. I'll just read this theorem. It's called the hinge theorem. It says, if two sides of one triangle are congruent to two sides of another triangle, so you can see here I've got this side is congruent to that side, and then this side is congruent to that side on two triangles. And if the included angle was be the angle between those two sides. And the included angle of the first triangle is greater, so if C is greater than F, then the third side of the first triangle is larger, so this would be the third side, is larger than the third side of the other triangle. It's called the hinge. Basically, if it was a door and this door was the same and this door was the same and you were just opening and closing, so if you opened it larger, then this would be a wider expanse. If you closed it, then this would be a shorter expanse. And then the converse of that is true, that says if two sides of one triangle are congruent to two sides of another triangle, and the third side of the first triangle is longer than the third side of the second triangle, then that means that the angle opposite of the third side of the first triangle is greater than the angle opposite of the third side of the second triangle. So go ahead and do that investigation because you will be seeing the hinge theorem and the converse hinge in other problems. Lesson 41, you did at home, but I didn't have time to do this in class. There was a lot of concepts covered. You're dealing with the ratio, proportions, cross products, and then the difference between similar figures, similar polygons, the transitive property of similarity, and just a similarity statement. So I do want to look at that last one, the similarity statement. If you have a four-sided polygon, ABCD, that if you're told that if it's similar to another polygon, EFGH, that these vertices must be listed in the order of correspondence. So A corresponds to E, B must correspond to F, C must correspond to G, and D must correspond to H. And that's what this is saying right here. So there was a couple of problems in here that I wanted to do. I actually have chosen 3. I don't know if I have time even in this video to do all of these because I don't want you to watch a very long video, but let's see. Let's look at this one. If the quadrilaterals at the right are similar, what is the measure of angle E? Let's make this bigger. And what is the length of segment XY? So here's angle E here, and we're told that they're similar. So since we're similar, we know that this has to correspond to this. So that means that angle E, I'm going to go ahead and write it. So the measure of angle E must be congruent to the measure of angle X based on that theorem that we just read. And that means since the measure of angle X is given to be 73 degrees, so that means angle E must be 73 degrees. Okay, and that's because that we are told that the quadrilaterals are similar. And that would be saying that the quadrilateral, let's say, W, X, Y, Z, and make sure I put it in order, is similar to, so I started here, and I went this direction. So I'd have to start with D and go that direction. So that means it's similar to quadrilateral D, E, F, G. So that definitely means that vertex X corresponds to vertex E. And that's how we can make that claim. The other thing says, what is the length of XY? So we're wanting to know this length here. What is the, well, we know the length of EF. Now, again, this is a little different. We know that when polygons are similar, let's review this. If similar polygons, what does that mean? Here, it means two things. It means, number one, that their corresponding vertices are congruent, but it doesn't mean that their corresponding sides are congruent. It does mean, though, that their corresponding sides are proportional or have equal ratios. You can say it either way. Okay, so we want to find the measure of, you don't have to put M like that. We want to find the measure of XY. Hold on. XY equals what? Okay, here's what we can say. We know the measure, let's see, do we have another side? Yes, we also know we have this measure here. Let me make it a different color. We know the side of WZ, and we know the side of DG, okay? So what we can say, we can make this whole relationship. We can go down here and say that WZ is to, I don't know if I should say WZ. Let's do it the right order. ZW, I'll do it in the order that it's listed. ZW divided by GD. I'm not going to put that bar over, it's too confusing. Will be equal to every side. I mean, I can do all of them. I can say it would be, that ratio would be equal to WX over DE, which is equal to XY over EF, which is equal to YZ over FG. We don't need all of those. We need to find XY. That's the one we're trying to find. We want to find this one. Well, which ones are given? Let's see. We're given WX, and we're told that WX equals 2. And we're given DG. We're given DG, which is GD, whatever. It's the same thing. And we're told that DG or GD is 3. And we're given EF, which is right here. And we're told that EF is 15. W, oh, this is the wrong one. This is WZ. I need WZ. Oh, I get it. I see what I did wrong. So that one was WX. WX was that one, WX over DE. Yes, this one here, I just had written it a different way, but this one is WZ. WZ is 2. Okay, so the good thing about this is I know these two values, I know one of these values, and I don't know the top value, so I can set these equal. So I'm going to solve for xy over 15 is equal to 2 over 3. Now I can, I really can cross multiply. I don't even have to cross multiply. All I really have to do is say times 15 on this side, times 15 on that side. That cancels, and then this leaves me with xy equals, I can see that 3 goes into 15 5 times, so then 2 times 5 is 10. So xy is 10. And that's how we find a side of a polygon using that theorem. Okay, compare the lengths of AB and DE. This is from Investigation 4. This is why you're supposed to do Investigation 4. It's using the hinge theorem. See, look, this is using the hinge theorem. Okay, what does the hinge theorem say? Well, here we're trying to find AB and we're comparing. So all we're going to say is, here's what we're doing. We're trying to say, is AB, is it greater than, less than, or equal to DE? Well, what does the hinge theorem say? It says that if you have two sides of a triangle that are congruent, so we have this side that's congruent to that side, they're both equal 15, and we have this side that's congruent to that side, they're both equal 10, and the included angle of C is greater than the included angle of F, so that means the opposite side of C is greater than the opposite side of F. So that means that AB is greater than DE. Determine the area of this metal plate. I don't think I'm going to do this one for you because I think you can see that all you would need to do is find the area of that rectangle, find the area of this triangle, and find the area of that smaller rectangle, and that would be the total area based on that one formula that you can divide up the areas into parts. So I will let you do that one because I don't think it's that hard to do. As long as you know the area of a rectangle is length times width, and you know the area of a triangle is 1/2 base times height. Then we previewed lesson 42 in class. I went over all that you see here. We went over that example in class. We went over that example in class. I did not do this example in class. Let's see what this one says. Finding the closest point on a line to a point. So given the equation right here, y equals 2x plus 1, and a point S, 3, 2, find the point on the line, and they're already showing you that it's here, but pretend you didn't have that written there. Find a point on the line that is closest to S. Well, what we've learned is the closest point of a point to a line is the perpendicular line that goes through that point that's perpendicular to the given line. So definitely it will be perpendicular. So how do we do this? Well, I wrote down some steps here. First, you're given a point and a line, and that is, here's the line you're given, and here's the point you're given. Then you find the slope of the line. How can we find the slope of this line? Well, I've already told you, look at the equation of the line. The slope is 2. So we know that this slope is 2. Then step 3 says, find the perpendicular slope of the perpendicular bisector through, in this case, not through P. Let me erase that. Not through P. In this case, through S. Okay? So how do you find the slope of a perpendicular bisector? You may not know the equation of this line yet that goes through that. But because it's perpendicular, you can find the slope. the slope will be perpendicular to the given line, which we learned was the negative reciprocal. So I do know the slope. So step 4 says from point, well, it says P, but it needs to say point S. From point S, let me erase this. From point S, use the perpendicular slope to find a point of intersection on the line. It shouldn't be, it's not the line S, it's the line T here. I think I cut and pasted this from something else. From T. So we know that the slope is -1/2. So that is the rise over the run. And it could either be positive rise over negative run or vice versa. So the way this is showing you here, it says we're going to go -2, that's the run, and +1, that's the rise. And it puts you on the given line right here. And that is the point of intersection. So the point of intersection here is, you can see it's 1, 3. You can just see from the graph that it's on 1, 3. Now what you're supposed to do is find the distance, because that's what it asks. How far is this? It's wanting you to find this distance here, D. Okay, so how do you find distance? So distance is equal to the square root. So you're finding the distance from T, which is 1, 3, to S, the point that was given, 3, 2. Because that's going to be the distance from the point to the line, because T is on the line. So you take the change in the x-coordinates, 1 minus 3, the change always means subtract, squared, plus the change in the y-coordinates, 3 minus 2, square, and that will be the square root of -2 squared plus 1 squared, which is the square root of 4 plus 1. So the distance is the square root of 5. And I don't know if the book wanted you to find a decimal point value for that or not, but anyway, that's what it is right there. I don't care what the book says, but that's the answer. Okay, and then there was this example 4. This is proving that all points on lines are equidistant. Hold on, I'm in lesson 40. I'm trying to figure out where I'm at. I need to turn there. 40, lesson 42, sorry. Give me a second. Example 4, I just want to make sure I'm there. Okay. We're supposed to prove that all points on lines are equidistant, because that was one of our theorems. Prove that if 2 lines are parallel, so here's 2 lines that are parallel in this example, then all points on one line are equidistant from the other line. So if I'm given a point on the line, and remember, the distance from a point to a line is always the perpendicular line, so I would draw it down and make sure it's perpendicular. So that distance from A to C will always be the same no matter where I'm at. So if I have a different point on that line M, say at B, if I drew the distance between that line, which is always perpendicular, and if I'm looking at that distance, which is those 2 distances, will be equal. So given parallel lines, you can see what's given. Given parallel lines, prove that segment AC is perpendicular to DB. All I'm going to do is go through this proof. So first we drew the diagram, and we have 2 parallel lines, and what it's telling you to do, because it wasn't given, but you're going to draw. The first thing you do after you draw the parallel lines, you draw a transversal, because we're going to use principles of transversals to prove this. So you draw a transversal from this point to that point right there. forming triangle ABC. So here we have triangle ABC and triangle D. I need to put it in the right order. So if I went ABC, I need to go DBC so that they're in the right order. Nope, that's not what I need to do. I did it wrong. It's DCB. Because we went A, B, C, so I need to go D, C, B, like that, to make them correspond. So we need to show that points A and C are the same distance apart as points B and C. So the first thing we're going to do, I don't know how to do this. I'm not sure how to do this. Let me see. I covered that up before, but how did I do that? Hold on. No, that's not what that is. What is that? Oh, that's what this is. No, how do I erase that? Oh, there we go. So first we have is that M is parallel to N, and that was given. So what is the next thing we can claim after that? Let's look over here at our diagram that we drew. We can see that angle CAB is congruent to angle BDC, and that's based on the definition of a straight line, or the distance between points. So we're going to say over here that angle CAB, like I just drew, is congruent, and in fact they're not just congruent. We're going to show later that they are 90 degrees right there. But what is the reason? The reason is that all right triangles are congruent. So I just showed that I have two sets of angles are congruent. Remember, I want to show that a part of one triangle is congruent to a part of another triangle. I'm trying to show, we never can forget what we're trying to show. We're trying to show that this part of triangle ABC is congruent to this part of triangle DCB. But first I have to show that the two triangles are congruent, and then I can claim that their corresponding parts are congruent. So to show that two triangles are congruent, we're either going to use side, side, side theorem, or side, angle, side, or angle, angle, side. These are theorems that let us prove that two triangles are congruent. So I've got one set of angles. I wonder if there's another set of angles. What about, let me go up here. What about angle ABC with angle DCB? See how these two are already drawn as congruent? They are congruent based on transversals and parallel lines, since the lines are parallel. So I can say that these two angles are equal because alternate interior angles are equal, are congruent, as long as you have parallel lines. And that's a second angle. So I've got these two going here. Can I show that there's a side that's equal? Not the one we're doing, that we're trying to prove. Is there another side? We're trying to prove that this side equals to that side. But can I show that either AB is congruent to CD, or BC is congruent to CB? Yes, this one is really the same line, and yet they are a part of both triangles. So I can go over here and say that BC is congruent to CB because it's the reflexive property, and I just showed that there's a third side that's congruent. So I have proven that the two triangles are congruent. Right here, I've proven that they are congruent. That's what we were trying to prove. So I can go over here and say triangle ABC is congruent to triangle DCB based on the angle side congruence theorem. And then now I can claim, since AC is corresponding to DB, then I can say that AC is congruent to DB based on this is called the corresponding parts, because those two parts are corresponding parts of, I just proved that they were congruent triangles, are congruent. So the corresponding parts are congruent as long as the two triangles are congruent. That's what that CP-CTC means. Okay, so it's proven. Lab 7 is part of lesson 42. You should also do that. And there's practice here that you should do as homework. I think these are very important because it's tactile. You're using your compass and ruler, and that's really good. I won't do that right here. But you're constructing a perpendicular line through a point not on the line. We did this part in class for lesson 43. We did this part in class for lesson 43. I did not have a chance to do example 4, and I'm not going to do, we didn't even do that. So this example 4 is applying properties of congruent chords. Let's see. Wait. 43. Oh, yeah. There was several theorems here. There was 4 theorems. We learned all these parts of a circle, chord, secant, tangent, and then there was 4 theorems that were really important that we learned. And one says, if a diameter is a perpendicular to a chord, then it bisects the chord and its arcs. So what that means is, if a diameter is perpendicular to a chord, then that diameter bisects these arcs. So those two are congruent and these two are congruent arcs. The second theorem says if a diameter here bisects a chord, that means it divides it into 2 equal parts, then it is perpendicular to the chord. The third one says that the perpendicular bisector of a chord, so here's a chord, and if I wanted something to bisect that chord and be perpendicular, like that, it will go through the center of the circle. And also the perpendicular bisector is also a diameter of the circle. And you know that the diameter always goes through the center of the circle. The last theorem says in a circle or congruent circles, chords that are equidistant from the center. So here's a chord, blue, and here's the center, and that distance is going to be the same as the distance from this second chord. So those two are the same. So if that's the case, then the 2 chords are congruent. That means the blue chord is the same length as the red chord. And also congruent chords, so if you have one chord and another chord that they're the same length, then you can guarantee that they are equidistant from the center. Okay, so if we look at this last problem, let's see, it's going to use 2 of those theorems anyway. Let's see if we can do this one. This is example 4. Okay. So if CD, let's go over here and highlight CD. If CD segment, no, we're finding CD. So we have to find CD that's red here. So if the length of AP, there's AP, is 5 units given, and the length of PE, this is 3 units, find CD. Okay, so here's what we know. We know that AB and CD, we know that they're equidistant from the center because of this little hash mark. So here's the hash mark. That one and that one proves that they are equidistant. Let me write that. I'm going to say a chord So, which is a segment. But chord AB, I better say chord so you understand. We're talking about chords. Chords A, B, and CD are equidistant. And that was given because of the tick marks. Okay? Now, based on theorem that we just read, theorem 43.4, based on that theorem, we know that AB is congruent to CD. That means they have the same length. Okay, so we know that. What we need to do, we need to find, we want to know the length. This is the one we're trying to find. We're trying to find this right here. That's what we're trying to find, the length of CD. So maybe if we could find the length of AB, we could know that what CD is. So let's go back and look at AB. Can we find the length of AB? Well, we know the length of AP here. I wish that was a different color. Maybe make it green? I don't know. We know AP and we know PE. I wonder if we could find AE. And we know that this distance is bisecting that chord. So this would equal that one. And then we can know what AB is. So let's first find AE. So we want to find AE. So we're looking at it and we can say use Pythagorean theorem. Okay, which says that the leg squared plus another leg squared is equal to the hypotenuse squared. And looking at that triangle over there, we see that one of the legs is 3. So that would be 3 squared. Plus the other leg is, I don't know, it's AE. It's segment AE squared is equal to the hypotenuse squared, which is 5. So I can solve for AE by saying AE squared is equal to 5 squared minus 3 squared, which is equal to 25 minus 9, which is equal to 16. But if I take the square root of both sides to solve for AE, then AE equals the square root of 16. So AE is, that's supposed to be square root of 16, is what? 4. So going over here, I know that AE is 4. But there was also a theorem that was theorem 43.1 that said that, you know, if you have a distance that is going to the center, then it bisects the chord. So we know that AE is half of that chord. So E has to be the midpoint of AB. Let's look at 43.1. What did 43.1 say? It says, if a diameter is perpendicular to a chord, then it bisects the chord. Well, this doesn't look like a diameter, but it is a diameter because it goes through the center. And if it's perpendicular, it is, then it bisects the chord. That's why we know that E is the midpoint of AB. So therefore, AB equals AE plus EB. and they are the same. AE equals EB. So that would be 4 plus 4. So AB is equal to 8. And since the segment AB is congruent to the segment CD, which is what we were trying to prove here, that AB is congruent to CD, now we can say that CD is 8 units. Now this is a very long video. I'm very sorry about that, but that's how much I prepared. That's for next week. So that's everything that I missed almost, and hopefully this is helpful.